The third way to fight deadlocks that is left is to avoid the olden wait. Simply put, we can devise a solution in which philosophers agree on who is going to eat next rather than on who gets a certain chopstick. You have such an approach presented here. We have one semaphore per philosopher, an extra semaphore called mutex, and an array of size n of states. One state can either be hungry, thinking, or eating. To enter and exit the critical section, we have two methods, enter CS and exit CS. In the enter CS method, each philosopher waits on the shared mutex variable. In other words, only one philosopher at a time can run the following two instructions, which change its state to hungry and call the help method. After calling signal on mutex, the philosopher running the entry CS method starts waiting for a signal on its entry of the S array. So how does the help function work? Only if the philosopher invoking it is hungry and his or her neighbors are not eating, then it changes the state of the philosopher invoking it to eating and sends a signal to it. Notice that since help runs in between a wait and signal on the shared variable mutex, if multiple neighboring philosophers try to change their state from hungry to eating, only one manages to do so. Once a philosopher is done eating, then he or she runs the exit CS method. Again, the relevant instructions are run inside a wait signal on the shared variable mutex. In this case, the philosopher sets his or her state to thinking and then helps his or her neighbors, trying to send them a signal they can use to enter their critical section, assuming they indeed want to. This solution is valid when it comes to mutual exclusion, and it also avoids deadlocks. Nonetheless, a process can start. As done before, try to reason formally about these properties. If you are interested in a solution that also ensures fairness, you can find a paper discussing it in the attached link.